Good day. For those of you who do not know me, my name is Douglas Harder, and this topic we're going to discuss the cross product. So in this topic, we will discuss finding a vector orthogonal to two given vectors. We will derive a general formula for finding such a vector using a system of linear equations and Gaussian elimination. We will then see the definition of the cross product and give a review of the right-hand rule, which you hopefully saw in secondary school. We will look at a means of memorizing the formula for the cross product, and then we will look at a number of properties of this product. Now, given two vectors u and v in R3, if u and v are not parallel, then these two vectors define a plane that passes through the origin. That plane must have a normal vector. We want to find this normal vector, or at least a normal vector. Now, that vector is going to be perpendicular to both u and v. So suppose that this perpendicular vector is the vector w, being w1, w2, and w3. Now, if w is perpendicular to both u and v, then both of these inner products must be 0. Now, those two inner products being 0 gives us two equations in three unknowns, w1, w2, and w3. These are those three equations, and as you can see, they're homogeneous. So now that we have two homogeneous linear equations in three unknowns, there must be infinitely many solutions. So how do we solve this system? We start with the augmented matrix, and we proceed to add negative v1 divided by u1 times row 1 onto row 2. That's going to put a 0 at entry 2, 1. And now we look at the second equation. Now, up until now, we have not used multiplying a row by a non-zero scalar. But let us assume that u1 is non-zero, otherwise we wouldn't be able to divide by it, and consequently we can multiply the second equation by u1. This gives us the following augmented matrix. All right. So we see immediately that this is in row echelon form and that there is a free variable. So now that this augmented matrix is in row echelon form, how did we normally go about solving? Well, what we would do is we would declare w3 to be a free variable, and we would then substitute w3 into the second equation and proceed to solve for w2 and then w1. However, we're going to do something slightly different. We're going to introduce a new free variable. So suppose we have the equation 3y plus 7z is equal to 0. Rather than declaring z to be the free variable, we will introduce a new free variable alpha, and we will declare that y is equal to negative 7 alpha, 7 being the coefficient of z in the equation, and z is equal to 3 alpha, 3 being the coefficient of y. Notice that if we substitute both of those values into the equation, we get negative 21 alpha plus 21 alpha is equal to 0, and that is true for all real alpha. Let's do this above. So w2 is going to be negative alpha times the coefficient of w3, which is at entry 2, 3. And w3 will be alpha times the coefficient of w2, which is the entry 2, 2. And we've expanded both of these and written them so that the u term comes first. We can now substitute both of these into equation 1 to get that u1 w1 plus u2 times our value for w2 plus u3 times our value for w3 is equal to 0. We can expand that out. However, you will notice that the second and fifth terms are the same, except the second or the fifth term is negated. Consequently, those two terms cancel each other out. Thus, we are left with this equation. Notice that we can solve for w1 by bringing everything else to the other side and dividing by u1. Thus, we have our solution. W is equal to alpha times this three-dimensional vector, the entries of which are various sums or differences of products of the entries of u and v. Now, we could choose alpha to be any value we want, but we're actually going to choose alpha is equal to 1. Using this, this defines what we will call the cross product of the vectors u and v. Now, notice that if we used alpha is equal to -1, then the vector would still be perpendicular to the plane containing u and v, but it would be pointing in the opposite direction. Graphically, if we have two vectors u and v, then the cross product u cross v is going to be a vector that is orthogonal to both. However, what we're also going to see is that if we calculate v cross u, that will also give us a vector that is orthogonal to both, but it will be pointing in the opposite direction. So one question we may have is, how do we determine which direction the cross product is going to be? Well, given the vectors u and v, we are going to see that there is, well, we know that there is a smallest angle between the two, and given this, we can then use something called the right-hand rule to determine which direction the cross product will point. You will recall that previously we chose to let alpha is equal to 1. Had we chosen alpha is equal to -1, then the cross product would be pointing in the other direction. So an easy way to remember which direction the cross product will point is to use something called the right-hand rule. So if we have two vectors u and v, and the angle theta is the smaller of the two angles between u and v, one will be greater than 180 degrees, the other one will be less than 180 degrees. Choosing the angle that's smaller, then if we point the index finger in the direction of u and the middle finger in the direction of v, then the direction of the thumb gives us the direction of the cross product. Alternatively, if we hold the fingers straight, pointing out, and that is in the direction of u, and we then curl the fingers in the direction of v, then the thumb will be pointing in the direction of the cross product. Once again, it's important that when we curl, we are curling in the direction of the smaller of the two angles. Now, this is an ugly formula to remember, and the right-hand rule doesn't really help. Here is a much nicer aide-mémoire for this formula. Notice that I have essentially an augmented matrix here. However, in the first row I have vectors. The unit vectors I, j, and k, and they are repeated. Then there are the coefficients or the entries of the vector u, again repeated, u1, u2, u3, then repeated, and then the final row has the coefficient or the entries of the vector v, v1, v2, v3, again repeated. What we're going to do is we're going to calculate the product of those three entries. So we have u2 times v3 times the first canonical base vector. We will then multiply the second canonical base vector times u3 times v1 and the third canonical base vector times u1 times v2. From this, we will subtract the first canonical vector times u3 times v2, the second canonical vector multiplied by u1 times u3, and the third canonical vector multiplied by u2 times v1. So, as you can see, the first entry there is u2 times u3 minus u3 times v2. The second entry, again, the second canonical vector is 0, 1, 0, has the terms u3 times v1 minus u1 times v3. And finally, the third canonical vector, 0, 0, 1, is multiplied by u1 times v2 minus u2 minus times v1. All right, so what is the cross product of these two vectors? Well, let's find the three entries. Here we write down essentially an augmented matrix, but in the first column are the three canonical basis vectors I, j, and k. The second row contains the entries of u duplicated, and the third row contains the entries of v, again duplicated. To calculate the first entry of the cross product, we multiply 0.1 times 0.7, which is 0.07, and we subtract from that the product of 1.5 and negative 0.3. The product of those two is negative 0.45, so we are essentially adding 0.07 plus 0.45, which is 0.52. To calculate the second entry, we multiply these terms associated with the second canonical basis vector. So 1.5 times 0.8 is 1.2. We subtract from that the product of negative 2.1 times 0.7. Well, negative 2.1 times 0.7 is negative 1.47. So 1.2 minus the negation of 1.47 is 1.2 plus 1.47, which is 2.67. For the third entry, we add or we multiply these terms, subtracting the second from the first. So negative 2.1 times negative 0.3 is 0.63, and 0.1 times 0.8 is 0.08. Consequently, we would have 0.65 minus 0.08, and that is equal to 0.55. All right, so now we have calculated the cross product of u and v, and if you were to work it out, you would find that u cross v is perpendicular to both u and v. Now, this is not multiplication. For first of all, multiplication is something that occurs within a field, and in a field, multiplication is commutative. So alpha times beta is equal to beta times alpha. However, this is an operation on vectors. we're going to claim that u cross v is equal to the negation of v cross u. Proof. Well, there is, by definition, u cross v. This, however, is v cross u. So essentially now, where there used to be the entries of u, we now have the entries of v, and where we had the entries of v, we now have the entries of u. The first step we will do is use the fact that scalar multiplication, or the multiplication of reals, is commutative, so we will rewrite it with the u terms first. What we will now do is factor out a -1 from each of the terms of that vector. That leaves us with that expression there, but you'll notice that that is the negation of u cross v. So v cross u is the negation of u cross v. And we're done. This property is described as being anti-symmetric. Recall that the inner product, however, was symmetric. It was also an operation on vectors, but the inner product of u and v was equal to the inner product of v and u, at least for real vectors. Now the cross product of the canonical basis vectors are as follows. I cross j is k, j cross k is I, and k cross I is j. Now you can see this and work this out for yourself if you want. For example, here we are trying to determine the cross product of I and j. So 1, 0, 0 appears twice in the second row, and 0, 1, 0, j appears twice in the third row. To calculate the cross product of I and j, we then observe that one and only one of the 6 products contains 2 1s and no 0s. And that is k times 1 times 1. So the cross product of I and j is indeed k. From the previous slide, you therefore know that j cross I must be negative k, and k cross j is equal to negative I, and I cross k is negative j. If you want, here's a very simple aide-mémoire as well. Consider this circle with I, j, and k at 0, 120, and 240 degrees. The rotation is as per a clock, and I cross j follows the arrows, so we get to k. J cross k equals I, and k cross I equals j. On the other hand, if we go counterclockwise, j cross I, therefore the result will be negative k. Also, we can use our aide-mémoire to determine that j cross I is negative k, as again there is only one product that contains 2 1s and therefore no 0s, and that is when we are subtracting 1 times 1 from the third entry. Another result is that the cross product with the 0 vector is the 0 vector. And this can be seen again from our aide-mémoire, because every single product has 1 0, at least 1 0 in it, and therefore every single product is equal to 0. Now recall that the real inner product was said to be bilinear, so it didn't matter whether or not you multiplied the first argument by alpha, that alpha came out of the inner product, or if you were to multiply the second argument by some scalar beta, that beta could also come out. Theorem: the cross product is also bilinear. So the cross product of alpha times u crossed with v is equal to alpha times the cross product of u and v. Similarly, u crossed with beta times v is equal to beta times the cross product of u and v. The proof is left to the viewer. This is simply an exercise of substituting alpha u1, alpha u2, and alpha u3 into the expression of the cross product, and you will see that an alpha does indeed factor out. And the same with beta. Now recall that for the real inner product, the absolute value of the inner product is the product of the two norms times cos theta, where theta is the angle between u and v. Theorem. It happens that the two norm of u cross v is the product of the two norms of u and v times sine of theta, where again theta is the angle between u and v. Proof. Well, the proof is in the course textbook, but it's long, tedious, and not much more than an exercise in algebraic proofs. Consequently, if you wish, you're welcome to go read through it. Now recall that field addition, field multiplication, and vector addition are all associative operations. And to show this, we had to show that this was true for all possible values in the field or in the vector space. Recall also that field subtraction, field division, and vector subtraction are all not associative. So in general, these relationships do not hold. To show that something is not associative, you simply have to give one counterexample. So in the first case, if you just set alpha, beta, and gamma all to be 1, the left-hand side is 1, the right-hand side is -1, and those are unequal. In the second case, we can set alpha, beta, and gamma all to be equal to 2, in which case the left-hand side is 2, whereas the right-hand side is 1/2. And in the third case, you simply have to let all vectors be any non-zero vector. So pick one vector, 1, 0, 0, let u, v, and w all equal that vector. The left-hand side will be that vector. The right-hand side will be the negation or the additive inverse of that vector. Claim. The cross product is not associative. We don't have to prove this in general. We just have to find one counterexample to show that this is the case. For example, if I take the cross product of I, and j, then I cross j is I cross k, and I cross k is -j. On the other hand, if we calculate it in this order, I cross I is the 0 vector, and the 0 vector crossed with anything is again the 0 vector. Thus we have our counterexample. Here are some other nice observations. So as the angle between u and v decreases, the magnitude of the cross product decreases. This is a consequence of the previous theorem. Thus, as the angle goes to 0, the cross product goes to 0. And in fact, the cross product of u and v is the 0 vector if and only if u and v are scalar multiples of each other. Finally, if u and v are already orthonormal, so at right angles and with unit length, then u cross v is also a unit vector or a normalized vector, and consequently u, v, and u cross v form an orthonormal basis for R3 automatically. Following this topic, you now understand the purpose of the cross product. Given two vectors that are not parallel, the cross product finds a third vector in R3 that is perpendicular to both of the first two vectors. You also understand how to find the cross product, and you have seen an interesting aide-mémoire for remembering the formula. You understand a number of properties about the cross product as well.
Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!